Hello. Today we will start the study of electricity. And let's start with a discussion on electric charge. What are electric charges? Everything you see around us are made of electric charges. In other words, electric charges are fundamental to nature. Electricity is fundamental to nature. Atoms, which are the basic constituents of matter, are made up of electrically charged particles. I'm sure most of you know what those electrically charged particles are. The two most important particles that make up the constitution of all matter are electrons and protons. Well, I'm sure most of you had a picture of electrons and protons. The protons are at the center of the atom, we call the nucleus, and electrons are moving around it. Alright, so there are positive charges and negative charges, but an atom, is an atom electrically charged? No, an atom is an electrically neutral object. Why? Because there are equal positive charges. The red balls are the positive charges, and the green balls really do not have a charge. They are the neutrons. So the total positive charge equal to the total negative charge. Therefore, the atom as a whole is an electrically neutral object. Protons, which are found at the core of an atom, carry a positive charge, and we will denote that by the small letter E. And actually, the small letter E we call the fundamental unit of electric charge. And we would assume that these positive charges are fixed to their relative positions. So they are not free to move about. We give the freedom of motion only to the electrons. So electrons are found moving in the space surrounding the core of the atom, and they carry a charge negative E. So if you have a proton of charge positive E with an electron of charge negative E, the net charge is 0. And in a normal atom, the number of positive charges will be equal to the number of negative charges. Now here I have a picture of the atom. The positive charges are concentrated at the center, and the negative charges are moving around it. Well, so that is a familiar picture of the atom. This is a neutral atom where the total amount of positive charge equal to the total amount of negative charge. Now tell me, by some means, if I'm able to take off an electron from there, then this atom will become a charged atom. Well, we will talk about that as we go on. So E is the fundamental unit of charge. This means that the charge carried by anything else comes in multiples of that E. All right. A proton and an electron together form a neutral object with no net electric charge. This means that a neutral object contains equal quantities of positive and negative charges. A neutral object does not mean that there are no electric charges at all. A neutral object is composed of equal quantities of positive and negative charges. Now, electric charge is measured in a unit called coulomb, and we will use the uppercase C to represent a coulomb. And a coulomb is a fairly high, fairly large unit. So for most practical purposes, we will be using millicoulomb, 1,000th of a coulomb, microcoulomb, 1,000,000th of a coulomb, 10 to the negative 6, nanocoulomb, 1 billionth of a coulomb, and so on. Most often we will be using microcoulomb 10 to the power of -6 of a coulomb, and nanocoulomb, that is 10 to the power of -9 of a coulomb. And the value of the fundamental charge, E, is 1.602 multiplied by 10 to the power of -19 coulombs. The charge carried by one electron is negative of that value. The charge carried by one proton is positive of that value. Alright, let's do a simple problem. A charge equal to the charge of Avogadro's number. Everybody recall that number, don't you? Avogadro's number? That is 6.02 times 10 to the 23 of protons is called a Faraday. So if you can find the total charge carried by all these protons, that amount of charge is called a Faraday. Calculate the number of coulombs in a Faraday. Well, that's a very simple thing. The charge of one proton is 1.602 times 10 to the -19 coulombs, and therefore what is the charge carried by these many protons? Multiply the charge on one proton by the number of protons. Now here you must see this is not 1023, it is 10 raised to the power of 23. So make that correction. So that will be 6.02 times 10 to the 23, the total number of protons, multiplied by the charge on one proton, and that will be 96,440 coulomb. That is called 1 Faraday. It's an important quantity in chemistry. Another one. How many coulombs of negative charge are there in 1 gram of copper? Well, in order to find the total amount of charge in 1 gram of copper, we need to figure out how many electrons are there. Now, is there any way to figure out the number of electrons in 1 gram of copper? Well, first of all, we start with the atomic mass. What is the atomic mass of copper? If you look at the periodic table, you find the atomic mass of copper is 63.5 grams. What does that mean? It means 1 mole of copper has a mass of 63.5 grams. So this means that the mass of 1 mole of copper is 63.5 grams. Now tell me, 1 mole of copper will contain how many atoms of copper? If you remember the mole concept, 1 mole of any substance will contain Avogadro number of atoms. So 1 mole of copper contains the Avogadro number, that is 6.02 times 10 to the 23 of atoms. So 63.5 grams of copper will contain this many number of atoms. Therefore, can you tell me, what is the number of atoms in 1 gram of copper? So look at this again. 63.5 grams of copper contains 6.02 times 10 to the 23 atoms. Therefore, how many atoms are contained in 1 gram of copper? Divide the total number of atoms by the total mass. Is that right? So the number of atoms in 1 gram of copper will be the total number of atoms divided by the mass of all that. That gives me 9.48 times 10 to the 21. There are so many atoms in 1 gram of copper. Well, how many electrons are there in 1 copper atom? Each copper atom carries 29 electrons. The atomic number of copper is 29. The periodic table will tell you that. So, the number of electrons in 1 gram is 9.48 times 10 to the 21 atoms. And each atom carries 29 electrons. Therefore, how many electrons are there in these many atoms? The total number of electrons is the number of electrons in 1 gram multiplied by the number of electrons in 1 atom. So that will be 9.48 times 10 to the 21. That's the total number of atoms. Multiply that with the number of electrons per atom. And that is 2.7 times 10 to the 23 electrons. Well, what are we looking for? We are looking for the total amount of charge in 1 gram of copper. Now, what is the charge carried by an electron? Well, the charge carried by an electron is 6.02 times 10 to the negative 19 coulomb. This is the charge carried by an electron. This is the total number of electrons in 1 gram of copper. So, the total negative charge will be 165,500 coulombs. You can see the extent of electric charge. 1 gram of copper contains a huge amount of electric charge. So we are actually living in huge quantities of electric charges. We ourselves are huge piles of electric charges. Is that right? Yes. Alright, let's now talk about conductors and insulators. What is the difference between conductors and insulators? Well, I told you earlier, protons are fixed to their relative positions, while electrons are free to move about. Well, in some materials, especially metals, electrons that are relatively at large distance from the center of the atom, that means from the positive part of the atom, are not very much connected, are very loosely bound to the atom, and they are virtually free to move about within the material. You see, that means a metal contains a large number of electrons that are loosely connected to the atoms. Which kind of electrons are they? The outer electrons. Now those electrons can wander from atom to atom, from one end of the metal to the other. That means the electric charges actually can move through such materials. Now such materials are called good conductors. Now let me see if I can show you a simple illustration on the web of that. Well, here is a good illustration of free electrons or loosely bound electrons in metals. You can see this electron in the outer part of the atom. It really don't have a sense of belonging to that atom because it is so far away from the central core. It can move from atom to atom. Do you see these electrons moving from atom to atom? That means there is almost what is called an electron cloud in a metal. Electrons are free to move about within a metal. Such a material is a good conductor. On the other hand, if this is not available, if there are no free electrons, electrons are not free to move within a material, then such materials will be called insulators. So all materials around us can be classified as good conductors and bad conductors. Alright, let's get out of here. Now, if there is some excess charge on this material, it will spread all over the material. What kind of material? On a good conductor. Now, the material I'm holding is actually aluminum. It's a very good conductor. If I place some excess charge, if I can get a bunch of electrons and keep it there, those electrons can travel right through the length of the material. So if some excess charge is placed on this material, that will spread right through the material. That is the sign of a conductor. A conductor will allow free charges to flow in it. Whereas if this is an insulator, for example, this is almost rubber insulator. If I place some excess charge on this, it will stay where I placed it. It will not be able to move along the material. Okay. So you got conductors where there are free electrons which are free to move within the material. Most metals are considered to be good conductors of electricity. In some other materials, electrons are localized or very firmly bound to the atoms and are not allowed to move from one part of the material to another. Such materials do not allow electric charges to flow through them, and they are called insulators. Now, both conductors and insulators are very useful for us. We are able to get electricity from the main supplies because we have carriers of electricity, good conductors. And we are saved from being shocked by all this electricity because we have good insulators. Is that right? So both conductors and insulators are an integral part of our life. Okay. Let's now talk about interaction between electric charges. How do electric charges interact? Now, I'm sure most of you have experienced the interaction between electric charges. Now, how do I get some electric charges free? Now, let me show you an illustration. I hope you can see. I have a little plastic ball suspended from, well, a stand, and I'm going to rub this plastic material by a little piece of wool. Now, what I'm doing is, because of the process of rubbing, some electrons will transfer from one material to the other. You see, materials differ in their electron affinity. When I do this process of rubbing, electrons from this strip of wool will transfer into this strip of plastic. That means this plastic will acquire some excess electric charge. And I'm holding it. And that excess charge will stay where I rubbed it because this plastic is an insulator. So, look at the way I'm going to create some excess charge there. I have created some excess charge there, and I'm going to bring it close to this plastic ball and see what happens. Oh boy. Now what happened? It was attracted, the ball was attracted, and the ball touched the plastic and it bounced away. Did you see that happen? Well, now, this plastic has negative charge because the wool has donated some electrons to it. Now, this ball came and touched that plastic. We would assume that the ball therefore also has some negative charge. Now what happens when I bring the plastic close to the ball? What happens? The ball goes away. What does that mean? You see that? Can you see the ball moves away? Yes. It means a negative charge does not like a negative charge. So, interaction between electric charges. What kind of interaction exists between electric charges? The fundamental properties of electric charges are like charges repelled. In other words, negative charge will repel a negative charge, and positive charge will repel a positive charge. Well, I have touched the little plastic ball, which obviously means that I have neutralized the object. Now, let's look at that again one more time. Now, when I bring the charged object, it gets attracted, the ball gets attracted, and obviously we would assume that the ball has acquired some negative charge. And now, if I bring that charge back to the ball, you can see the ball goes away. A negative charge repels a negative charge. Right. Okay. Unlike charges attract, on the other hand, if I can create some positive charge, I don't think I have something here which I can create a positive charge with. Let me see if I can get some positive charge. There you are. I actually created some positive charge. What happened? The positive charge attracted the negative charge. There you are. See that? So, unlike charges attract, a positive charge will attract a negative charge and will move towards each other because of the attraction they have for each other. So these are very important properties. We have like charges. Two negative charges will repel each other. Two positive charges will repel each other. On the other hand, a positive charge will attract a negative charge. I have illustrated that over here. A positive charge, just same kind of ball that I used. A negative charge and a positive charge will attract. Two negatives will repel. Two positives also will repel. Okay. Now, how do we know if an object has some excess charge? Let me move this out of here. How do you know if an object has some excess charge? Well, we can use something called an electroscope. An electroscope. What is an electroscope? Now, let me see if I can show you an electroscope. Again, I'm just taking a chance. I don't know whether you can see it, but if you can see it, I want to take that away from the screen. Give me a second. Okay, so I have the electroscope over here. Let's see what an electroscope is made of. An electroscope has a conducting platform. Well, if I want to call that the platform. It has a conducting stem, if you see the stem there, and it may be difficult for you to see. There are two leaves. The leaves sort of come down. Now, how is it useful? If I can charge both these leaves with similar charges, they will repel and move away from each other. So what are the parts of an electroscope? It has a conducting platform, it has got a conducting stem, and two conducting very thin leaves. If I place some excess charge on the platform, because the platform is a good conductor, and the stem also is a good conductor, these excess charges will flow, will spread right through and reach the two leaves. And the two leaves will get similar charges, they will move away from each other. Is that right? Now, let me see if I can show that to you. If I can get this charged. Now, let's see if the leaves of the electroscope will move away. Watch this. Well, it didn't happen very much, but you can see actually something did happen. Let me try one more time. I'm trying to produce some excess charges on this. There you are. Did you see? The electroscope now is charged and the leaves are diverged. That means the electroscope now has some negative charge. Can you tell me what will happen to the charge on the electroscope? What will happen to the leaves if I now take this negative charge near the electroscope? Now I want you to watch this. I'm taking the charge near the electroscope. Well, you don't see anything happen, is that right? Okay. Okay, you can see I have the electroscope charged and I have the negative charge in my hand. See what happens when the negative charge is taken close to it. Well, what happens? Actually, the divergence increased a bit. Why? Because the electroscope actually carries, the leaves actually carries negative charge. When the negatively charged object is brought near the platform of the electroscope, the negative charges inside here do not like the presence of this negative charge. They go down to the leaves, producing further divergence. Well, let's have a look at what the interaction. Give me a second to bring back our slide. So that's our electroscope. What is an electroscope used for? You can see the diagram here is slightly different. That is the conducting platform, that is the conducting stem, and this is the leaf. And for this there is only one leaf. This is not movable. In my model, both leaves can move, whereas here only one can move. And when you keep some excess charge there, it will spread through the stem and the leaf, and this part of the stem will have the same kind of charge. The leaf will diverge. And actually, here's a scale. You can measure the extent of divergence. That will give you a measure of the amount of excess charge. Alright, we talked about all that. Now, if some excess charge is placed on the platform, then it spreads onto the stem and the leaves as they are conducting. So I'm going to move this away. Let's do without a model now. As the leaves and the stem acquire similar charges, the leaves move away from the stem, producing a divergence. You can see, well, see what happens when this gets negatively, well, you can see the negative charges there and the leaves diverge. What happens when you touch it? Touching is the process by taking away. You see, if you touch a charged object, it gets neutralized. The excess negative charge on this electroscope produced a divergence, and when you touch it, those excess charges, you see, your body is a good conductor. That means if you touch a charged object, the charges can move through your body to the earth. That's what happened here. Okay, so as the leaves and the stem acquire similar charges, the leaves move away from the stem, producing a divergence. In the same way, I want you to watch this. This is a positively charged electroscope. What happens when you touch it? Can positive charges move down to the earth? No. What happens is the negative charges from the earth move to the electroscope, neutralizing the positive charge on the electroscope. You must understand that only negative charges are free to move. So, if a negatively charged electroscope is grounded, grounded means you touch it, then the negative charges will flow through your body to the earth. On the other hand, if a positively charged electroscope is grounded, the negative charges from the ground will come in, neutralizing all the positive charges. The electroscope is now neutral. Okay. Let's now talk about charging an object either positively or negatively. Now, what is the meaning of charging an object either positively or negatively? Generally, all objects are neutral, which means that they contain equal quantities of positive and negative charges. If some negative charges are removed from an object, just like we did here, what did we do here? When you rub the plastic rod with the wool, what happens is some electrons are removed from the wool. That means this material is now deficient in some electrons. That means there is some excess positive charge on this material. And the electrons that are removed have been deposited on the plastic strip. That means the plastic strip now has some excess negative charge. So, a positively charged object has some excess positive charge on it. If some negative charges are added to an object, it has an excess amount of negative charge. So, depending on whether you have some excess amount of positive charge or excess amount of negative charge, we have a positively charged object or a negatively charged object. Remember that the total amount of electric charge in the universe is a constant. That means if one object loses charge, then another object must take over it. Is that right? When the piece of wool loses the electrons, the plastic strip will receive them. So the total amount of charge is a constant. We call it the conservation of electric charge. So this is called the principle of conservation of electric charge. If two objects form a closed system, that means the total amount of charge they hold will remain a constant, even though charges could flow from one object to the other. The amount of charge lost by one object will be equal to the amount of charge received by the other object. Alright. Charging an object either positively or negatively. When a polythene rod is rubbed with fur. Well, that's what I just showed you. It is observed that the plastic rod acquires some negative charge. Well, what happened is, this is my piece of fur. So, a good number of electrons have been removed from the piece of fur or wool. Both will do the same thing, a piece of wool. That means the wool is now positively charged and the plastic strip is now negatively charged. So this is made possible by electrons getting transferred from the fur to the plastic, leaving the fur or the wool positively charged and giving an excess amount of negative charge for the plastic rod. In the same way, if a glass rod is rubbed with silk, I showed that to you too. Now, in this case, the glass rod will lose electrons to silk. Silk will receive electrons, glass rod will lose electrons, which means what will be the type of excess charge on the glass rod? The glass rod acquires an excess positive charge and the silk will retain a net negative charge. Well, so here I have an object that has a net positive charge. So by doing this, you can actually create objects that have excess positive charge or excess negative charge. You see, even you can create excess charge by simply rubbing some of these onto your hair. Let's see if I can produce excess charge by rubbing a piece of a pen, for example. Well, this may not work, but try this. I'm going to rub this pen onto my hair and let's see if the plastic ball is going to react to this. Well, very weak, but there is some reaction. What is the rubbing doing? You can see a little attraction is there, yes. Well, the rubbing is removing electrons from my hair and depositing it on the pen. Okay. So, that means a positively charged object has some excess positive charge and a negatively charged object has some excess negative charge. The Earth is a large reservoir of electric charges. That means no matter how much electric charge an object has, if you connect it to the earth, that object will get neutralized. If a negatively charged object is connected to the earth, the excess negative charges will flow to the earth. On the other hand, if a positively charged object is connected to the earth, negative charges from the earth will flow into that positively charged object, neutralizing all the positive charges. Now, whatever method, the result of connecting a charged object to the ground is that the charged object will get neutralized. Now, in order to neutralize an object, what all you need to do is touch that object. Now, let me see if I can show that to you. But you see, these kind of experiments will work only in a very dry climate. Let me see if I can charge the electroscope one more time. Give me a second. It takes a little patience to do that. So, if I can charge this electroscope, there you are, and see what happens when I touch it. You can see the leaf simply collapsed. So, a charged object will get neutralized when you ground it. The process of touching is actually connecting the charged object to the ground. So this process is called grounding, and we use a symbol for grounding. Look at this. This is the symbol used for grounding. In any electrical circuit, if you see this symbol, that means at that point the electrical connection has been made to the ground. Alright? So the symbol for grounding. Now, there are two ways you can charge a neutral object by using a charged object. You see, suppose I have a charged object. Now, I produce excess charge on this. Here I have a charged object. Now, I want to charge the electroscope. Now, what do? What all I need to do is bring this charged object and make contact with the neutral object. I'm making contact, that means the same kind of charges. These negative charges have flown into the electroscope. The electroscope has acquired the same type of charge. And touch it is neutralized. So charging by conduction means bring a charged object, this is the negative charge there, bring a charged object and make contact with the neutral object. This is the electroscope actually. And when you make contact, some of the excess charges will flow into the electroscope. Now you can see the electroscope has an excess charge. Now that's how you charge by conduction. This process by which you make contact between the charged object and the neutral object is called charging by conduction. Now, this time we used a negative charge to charge the electroscope negatively. Alright? Okay. Now, what happens if you bring a positively charged object near the electroscope? Now, this time, it is not these positive charges that are going to move into the neutral object, but the electrons or the negative charges from the neutral object is going to flow into the charged object. Now remember, for every electron that moves from the neutral object to the charged object, a positive charge will be left on its own. Can you understand that? Every time an electron moves from the neutral object to the charged object, an excess positive charge will be created there. In other words, you can therefore say it is equivalent to a positive charge from here moving over here, although it is not exactly what happened. What actually happened is an electron from the neutral object moved and neutralized a positive charge there. In doing so, a positive charge was created there. That means at the end, the net result is this neutral object get positively charged. I hope you understood the mechanism there. Now, there is a second way of charging. It's called charging by induction. What is the meaning of to induce? Now, in induction, there is no physical contact made. No physical contact made. Now, let me see if I can show that to you. It may not work, but it doesn't work, doesn't matter. If I bring a charged object near the electroscope, let's see what happens. I'm trying my best to charge it. All right? I'm rubbing it very furiously. Now, bring it close to the electroscope, but don't touch it. Now, can you see what happens? I haven't touched it, but the leaves are diverging. Can you tell me what happens? Let's not do any drawing or writing. I want you to talk about it. I brought this negatively charged object near the electroscope. I see the leaves diverging. Why? Well, because the negative charges in the electroscope do not like the presence of this negative charge. So they move down to the leaves. What happens is the leaves get an accumulation of negative charges, which means the top of the electroscope is now positively charged. Now, this process is actually called polarization. Now, let me illustrate that on a small diagram. Give me a second. Now, what happened here is, this is the neutral object, and here I brought a negatively charged object near it. You see? We have a neutral object here, and a negatively charged object is placed near it. As a result, you see, at this end, you can see there are so many negative charges there. The negative charges at this end do not like this negative charge there, because a negative always repels a negative. So a lot of negative charges from here will move to the other end. That means that end will now have an accumulation of negative charge. But remember, each time a negative charge moves away from this end, a positive charge is created there. So there will be an accumulation of positive charge at that end. So the net result is, by bringing a negatively charged object, it will also happen if you bring a positively charged object near a neutral object, what we have achieved is, inside the neutral object there is a splitting of electric charge. You see, these like charges moved away, unlike charges stayed close by. This process of splitting electric charges within a neutral object due to the presence of a charged object is called polarization. Polarization. You see, it is similar to the polarization that takes place in a political party. Is that right? When you have differences of opinion, one set of people with one opinion move to one direction, other set of people move the other direction. We say there has been a polarization in the party, almost a split. And that's exactly this happens. So, here, when I bring a charged object, let me see if I can charge it again. Alright, when I bring a charged object near a neutral object, do you see what happened? What happened is, many negative charges do not like to stay on top. They all went down to the leaves, making the leaves diverge. Polarization of charges. Okay, let me close this. Now, the first step in charging an electroscope by induction is, bring a positively charged or negatively charged. Now, I have written here positively charged. and I'm going to use a negative charge to illustrate it. Close to the electroscope platform without touching it. What happens? Because of the presence of these positive charges, a lot of negative charges from the leaves will go up to the platform. There is an accumulation of negative charges at the platform and an accumulation of positive charges at the leaves. Now remember, when I bring a negatively charged object close to it, the process is reversed. Alright, so that's the first step. What is the next step? We actually talked about it. The process is called polarization. Here, polarization has happened. Now the leaves diverge due to the presence of excess charge in it. What is the second step? Ground the conductor by touching it. Now tell me what happens when you ground the conductor. When you ground the conductor, well, you notice that these negative charges are held here by these positive charges, and they will not go to the ground. So, what happens is, negative charges from the ground will come up, and those extra charges coming from the ground will come and neutralize the excess positive charge on the leaves. The leaves will then collapse. Alright, what do you do now? Remove the grounding. Now when you remove the grounding, what actually happened is, because of the grounding, the excess charge on the leaves have disappeared. When you remove the grounding, the electroscope is now left with this excess charge. What you see here is now excess charge. If you remove this charged object, what will happen? These excess charges will spread and giving the electroscope an excess negative charge. Alright, let's see if I can practice this over here. But in my discussion here, I used a positively charged object, bringing close to a neutral electroscope. And in my demonstration, I'm going to use a negatively charged object. Let me see if I can, how best I can charge it negatively. Alright, I'm trying my best. Let's see what we can do. Now, do you remember the first step? Well, the first step is bring a charged object near the platform of a neutral electroscope. So I'm going to bring this charged object, I hope it is charged, near the neutral electroscope. Well, I don't see, well, not very much is happened. And earth the electroscope. Alright, now remove the earthing and remove the charged electroscope. You can see there is a slight divergence on the leaves, and you can see if I touch it, it converges. Well, the electroscope got charged by induction. So the various steps of charging an object by induction. Okay. Now I want you to watch these steps. Look at the bring a negatively charged object. Polarization has happened. Negative charges moved away. Now ground the conductor. The negative charges have moved down to the earth. Now remove the charged object. Alright? Leaving this neutral conductor with some excess charge. Let's do that again. Step 1. This is a neutral object. Bring a charged object near a neutral object. What happens? Polarization. Like charges move away, and now ground the neutral conductor. Those charges are all gone down to the earth. And now remove the charged object. Alright? The electroscope or the object is now left with some excess charge. Now this is how you charge an object by induction. A neutral object is charged by induction. I hope you will be able to remember these steps. Okay. There you are. Alright, let's move on. I want you to watch this one. There are two neutral conductors in contact. You bring a negatively charged object. Look at here now. Polarization happened. And somebody came and removed the second object. And now the charged object is removed. You can see this is negatively charged and that is positively charged. I want you to watch this. I'm going to run this 2 more times. Look at it and write a paragraph about this and email it to me. Alright, extra credits. Watch it again. Okay, watch from the beginning. Two neutral conductors in contact. Bring a charged object near. Polarization happens. Move one conductor away. Now, remember, this part is insulated, therefore earthing does not happen. And you can see, because of the polarization, this now retains negative charge and that retains positive charge. A very interesting phenomenon. So write a small paragraph about it and email it to me, and that will be extra credit for you. Now, our next part of study is Coulomb's law, which I'm going to do as a separate lesson or a second part of this lesson. Since it's going to include some calculations, I want to start fresh. So today's lesson, I'm going to close this one here. Watch this carefully and learn about the interactions of electric charges. Alright? I will see you with a second part of this lesson later on.